Welcome all of you. We will start now. Hope you can hear me and see the screen. Okay. As I mentioned, we are going to see again multiple processes, but it is a little different from multi-threading that we learned in the last two classes. Let me start off just an introduction. We have a process, and then I said that what is executing inside the process are multiple threads. And then I also said that the threads have access to the data code of the process, the parent process. Now, you know that a process is a single entity which is executing in a CPU. And when we want this execution of instructions, which is a sequence of instructions, we want to stop it. Then I told that we need to save the register content and then any other status information about the process or number of files open and any IO port they have tried to read from, they have kept it open. Those things are saved. And then a new process or a new thread is brought into the picture or into the CPU. So if you look at the CPU, imagine that CPU is having only one set of registers. We are not thinking about hyper-threading feature of a CPU. Then there can be only one process or maybe one of the threads possibly can be running in the CPU. So what is the difference between a process and a thread? From the status perspective, from the CPU context perspective, both are same, because you cannot have when I said that parent process is running and the child is another thread, can the thread T1 run along with the process in the same CPU? No, it's not possible because they are two different instances. So parent is different from a child. Only thing is the child is living in the context of the process. When I say it is living in the context of the process, it's like our parents living with us. We are still different entities. Children are different entities. Parents are different entities. We all live in a house. We share everything, but individually we have our own food we eat. We can't eat in the parents' plate, and then maybe we can do that. But we have our own life inside the house. So process is like the place wherein everything is allowed to be shared between the multiple threads. We call them as siblings, but they still have their own life, their own status, which is the CPU context in particular. Now, the multi-threading or a threading, just a threading module that we learned helps us to create multiple threads in the context of the process. So they all run in the context of the process. When I say context, they share the data, code, everything. So that is a multi-threading. Even that is also a multiple instances of different things happening, and we can have them running on different CPUs also. It's not that, please remember, just because they are sharing the process, they don't need to be running on the same CPU. If you have a 4 cores and each of them having multiple threads, hyper-threading like what I have, one T1 can be running on here, maybe using one of the threads, maybe T2 may be running here, maybe parent process status is running here, and maybe T3 can be running here, like this scenario. They can occupy any CPU. Now, what is the advantage of when the threads belonging to the same process running in the CPU? Okay, this is our CPU, set of CPUs. It's not only one CPU, 4 CPUs. They individually have their own cache, but when you come down to different cache levels, now many of the processors have C1 cache level 1, level 2 are inside the processor. L3 cache or maybe L4 also, they are shared between the CPU. Now imagine, I'm not talking about this, maybe L3 is cache. This will be shared between the cores. Now, when I say that threads on the parent process belonging to the same uh, process running on the multiple cores in the CPU, they can share this cache memory. The code could be the same. Maybe they will be executing different parts of the code, but they will be sharing the memory. And then L3 cache, okay, and then we have a main memory. So main memory also can be shared. Code may be residing here and data may be here, but individual threads may have different stack, S1, S2, S3, but all of them are actually, if they are all running in the same time, they are actually sharing most of the things in the cache and most of the times in main memory. So we get the advantage of multiple uh, threads of belonging to the same process running in the CPU in terms of optimization in terms of cache and main memory, because we don't have to shuttle between the main memory and the disk more often, because main memory can accommodate all the code and data which is being shared. So these are all good when we want to do something within the process. Now, what if I want to create two different processes? Okay, let me call them as P1 and P2. Still, they can have their own threads. Okay, nobody stops you from creating multiple threads within the process. But now we are not talking about that. But you can still don't think that if I have multiple processes, multiple threads can't be there. Both can be there. But to simplify the things to explain, I am not going to create multiple threads within the process, which you are free to do it. Okay, so there are two different entities, like two different houses, okay, on the same street, because they are sharing the same CPU. Now what happens when you have two different processes? They have their own CPU. Maybe you can say that CPU core is running, or maybe one of the thread P1 is running. Imagine that there is another core where one of the threads is running the P2. Now the issue is not the issue, but not the what is happening here is each of those cache, whatever we have, level 1 cache, level 2 cache of these processes, they will be now having different part of the main memory, because within the main memory, this is the P1's area, maybe data code stack, everything is there, and this is the P2's area. They map to different set of memory. Now when we have a main memory which is belonging to two different processes, they reside in a different parts of the memory, then the cache what is being shared, maybe L3 cache is shared between all the cores. Now this space here will be now shared by the different parts of the memory. Now you know that cache has a limited space. Maybe it is 128 MB or whatever. Nowadays caches are much bigger than what we had 10 years back. This is in gigabyte range. This is can be MB range. L3 can be, L1, L2 can be in kilobyte range. So, and then each of the blocks in the cache will be of maybe 128 bytes or maybe here 256 bytes or something. So you bring in small blocks here, and when they are competing from two different locations, this cache will be inefficient, in the sense they need to write back into the memory and then get back another block or cache line into the cache. So what happens is multiple processes running the CPU, when they share the CPU, lots of activities happen between the memory and the CPUs and the cache. So it's not more efficient compared to the multiple threads of a single process running in the CPU. So understand the difference between how they impact finally when they run on the CPU. So when you are developing any application, if you have an option either to have multi-threading, why I am explaining all this is because you need to think about the hardware underneath when you have an option to either do a multi-processing or multi-threading. Okay, if it is an application which is lots of things are shared between them, and they do maybe some may be doing file handling, some may be doing some machine learning algorithm they run, and then maybe one is displaying out display task. So if they are operating on the same set of files, and they they work on the common goal, then making them multi-threaded is advantageous, as I explained to you the reason behind it, because if they are running on the CPU at the same time, they will be having only one set of memory being accessed, block of memory, and the cache and other things are being shared. So we'll have much more efficient way of managing them, and they will run on the CPU much better than they are multiprocessing. The same thing if you do it on multiprocessing, they will be having the issues because you have to share some files, because suppose the ML algorithm is running here, and then maybe compression or decompression is running here, but they operate on the same file. Then you need to provide some lock, maybe shared memory in the region where two processes are accessing them. Lots of things you need to take care at the OS level, and which will not be more efficient in terms of execution also. But what you gain is the total independence. This process misbehaving will not impact it. Okay, totally they will be isolated. OS will take care of making sure that one crashing doesn't stop other fellow from running. So that kind of safety measures you'll have. But if it is a common application, I would say multi-threading would be a better option. But I don't take it as a hard rule. It depends on what application you are running and how it is going to be sharing information. All those things you need to keep in mind when you decide whether to build a system using multi-threading or multiprocessing. But knowing both and knowing the differences between them and the advantages of each and how they impact at the hardware level will help you in deciding about which one to go for when you really design the system. Okay, so effectively what I'm telling is now we are going to learn about multiprocessing and what does the Python uh, APIs provide to help us implement some multiprocessing, how to create processes, how to run them. Okay, that's what, and how to communicate between them. That's what I'm going to show you today. Okay, any questions on what I explained here? Anybody? I presume everything is clear or nothing is clear, only Boolean, but I'm sure you guys are following. Fine. Now let me run through it. That introduction is enough. This is what maybe capturing the in a nutshell of what I was telling you. Now, which is multiprocessing and which is multi-threading. Okay, thread is there, so it's multi-threading. Now here what is happening is only one thread is running. Okay, see, remember, even the process itself is a thread. That's why I call it is a main thread. Okay, that's why there is a subtle difference between the main thread and the children. Okay, the reason being, main, there is nothing like it has a very high level accessibility or whatever. All of them have equal rights within the process, but main thread decides to create the children. Okay, that's how the responsibilities lie. But the access to the data and code or whatever, they all share it. Okay, it's like maybe the main thread, like in our house, maybe they may have a separate bank account and access to the bank account. Maybe children may not have until they become adults access to that, but everything is being shared, right? So similarly, this main thread is what lives along with this, but it has the creation of this children thread and then child, and then they also can wait for this thread to end their job and join. All those things the main thread can do. Okay, and we, in fact, we saw that even the siblings also can wait for some other thread to join. Okay, it's allowed because we are sharing the same objects. Okay, anybody can do it. Okay, it is again a language or OS specific, whether some OSs may not agree, allow you to do it, but in the Python world, when you create it, anybody can wait on any thread, which we demonstrated it in the one of the classes in this week. So this is about multi-threading. They okay, except one thing, which is stack. Each of those threads, they have their own stack. Okay, that you remember, because though code is common, when they call F1 is calling F2 and then F2 is calling F3, a thread T1 doing this sequence, all the status of that will be captured in the stack of thread 1. Okay, let me call it as stack 1. Whereas a T2 thread is doing the same sequence of function calls, they will be in the stack 2. Okay, it will be in different memory. So you can pass this F1 with some parameter 1 for T1. Maybe when I call same function with from the thread 2, I may pass a parameter which is 2. So the sequence, whatever is happening and what parameters you pass and how the internal processing is happening within those functions, if there are local variables, and the maybe in T1 F1 may call F2, whereas in the T2 flow F1 may call maybe F4, and then maybe calling F3. So the sequence of activities that is happening between multiple threads may be different, but they are all executing the same code F1, F2, F3, which is there in the code area. That's why I said that memory is shared, code memory is shared, the stack is shared, the caches are shared. Sorry, not stack, cache memories are shared. But when it comes to stack, they all have different stack. That's how they show different entities. Okay, different instances. So the stack memory of each of them are separate. That's why it is shown like this, and registers are different, but code data is common and files are common. So this picture exactly captures what are being shared between threads and what is unique between the threads. Okay, this you should have a clear idea whenever any interviews. If you are not very clear about it, then there will be issues in getting into, especially companies like semiconductor companies, where they look for your knowledge on hardware. Also, you need to be stronger there. Okay, so I urge you to learn something about some architectures and OS fundamentals, which are very essential. Just knowing a Python language may not be sufficient. You need to have the global view of how things work finally on the system, because then only you will be a good system designer and should be able to write a very good program. More than writing it, debugging is an issue where if you do not have this background fundamental knowledge underneath what is happening, debugging will be a nightmare. And especially when you are into a company and you are having a big code base and things don't work and bugs are coming up and customer is behind you, then you realize the strong fundamental only can save you there to identify the problem and fix it, and your fix also will be perfect. Otherwise you will open up some new bugs without knowing if you try to fix it. So they are very important when you actually work on in a company with a big code base. Especially they will be having multi-threading and multiprocessing in them. Okay, so even networking will come, but okay, at least this will help you out to learn more about it. Now let me just summarize in one slide. Multiprocessing is a package that supports spawning of processes. When you say we create threads, we spawn process. Okay, uh, create thread is a simpler job, but spawning a process is a little more involved from the OS perspective also. The reason being, if you look at Linux, they do a lot many job when they do fork and then when you do exec, because it's a bigger job from the OS perspective. That process has much more information, which I explained to you earlier, file handling and all the which process is owning which file, and how much they have access to the file. There is and then the memory is different, so they have to configure the MMU and then bring all that images of those executable from the hard disk and put it on the memory. So it's a huge job from the OS perspective, and it takes a lot of time also. So spawning of processes is not as simple as creating a thread within a process. So that is also a major difference that you should know from the performance perspective. So, but it is similar to threading module. Okay, it allows you to have multiple execution units. So the multiprocessing package supports spawning of processes. It refers to a function that loads and executes a new child process. So what it means is, it's maybe for you from a Python perspective, it could be just a function. Okay, but internally when you think about it, they are different. Okay, though it's a simple function call, a thread calling this function and a process calling this function, they are different in the sense, before even they call, a lot of work has happened in the background, and which is much more time involved compared to creating a thread. So the multiprocessing package, now this is what I was talking about earlier, global interpreter lock. See, when you have, okay, that is more important from the Python perspective. Let me bring out the difference between multiprocessing and multi-threading from the Python perspective. Now, when you have P1 and P2, two different processes, they are running on two different Python interpreters. Okay, interpreters. That means PVMs are different. Okay, this is running under different PVM. So even the PVM, you need to invoke the Python exe to bring a new process into life. Whereas if you are creating new thread, you will not create another exe in the same thing. These threads are running. Okay, they are sharing even the PVM. Okay, now what is the problem when you share the PVM or the interpreter, one Python interpreter? See, Python exe is one interpreter. Yeah, I'll be calling here and creating a process. And because Python cannot run like an any C executable, suppose if you are running a C code executable hello world program, it has a complete image of the process, and that file can be hello world exe, can be a.out or whatever you call it as, that can be taken out and laid out on the main memory, and it can be run. Whereas for you to run your Python program, you need the PVM, you need the Python exe. So when you create multiple processes, multiple Python exes are run. So they run in a different world because they run in a different PVMs. Now, when two processes are running on two different PVMs, okay, I'm not talking about multi-threading now. When these two are running, and this PVM is going to use its own C library, okay, it is have a separate, they are not clashing with those C library is common. It could be common between these two EXEs because the shared libraries, but still they run individually, right? So this global interpreter lock, which I mentioned, that some of those C library, see, Python itself is implemented as C in C, right? So those, they are not actually equipped for multi-threading or multi-processing. I said that we need to use this interpreter lock, global interpreter lock, to protect it against. So when you have multi-threading, they we use the this locks if they are accessing some common database. So there may be some performance impact due to that. Okay, GIL being active, GIL will be used when you have multi-threading within the process because they run on the same PVM instance. Whereas if you have two different processes, there is no impact of GIL because we are not competing against anything, because this is imagining that only one process thread is running here. It will run without any issue. Okay, though it will use the GIL, it will immediately get the lock will be used by only one guy. So even if it wants to get the lock, if only one person is entering the house, you don't need to wait for someone else being there, right? So in a locker, suppose bank locker, you are the only fellow who owns all the locker in the bank, then of course you must be very rich to own all of them, but you can enter into the locker room and the bank anytime you want. Nobody is going to stop you from entering there because you own the whole thing. So that's why I said that if you are using only one process, only one instance execution unit, you can use the PVM anytime you want the lock. It's available and you use it free, no problem. Whereas if you have multi-threading within one process, they need to compete for the lock. GIL as a performance impact when you have a multi-threading in the thread. So you should remember this impact also when you decide about how things work. Okay, so the multiprocessing package offers both local and remote concurrency, in the sense you can even decide to run it on some other machine, server machine or any other machine, remotely log in and then you run one process there. You can spawn one process there. So effectively sidestepping the global interpreter lock, because we are not going to be worried about GIL at all, because they are running in two different instances of the PVM. So they don't need to worry about GIL when they are running in parallel. So by using subprocesses instead of threads. So you can use subprocesses instead of threads if you don't want this GIL to interfere with your performance. Okay, but you need to think about all those CPU, memory, cache related advantages, all that I told you. So there are always some give and take. Nothing is there is no free lunch. So you have to give up something to get something. Now, due to this, multiprocessing module allows the programmer to fully leverage multiple processes on a given machine. So, this is another because no thread is if suppose you are running P1 here and another CPU core is running P2, except that I told you that main memory and yeah, maybe the common L3 cache may be sharing the memory. Okay, you may be having some competing cache lines, but the lock is available always. So this P1 is not going to be stopped for any reason. Okay, if you suppose the CPU is available and the scheduler OS scheduler is nice enough for you to occupy the CPU forever, then P1 and P2 can run continuously on two different cores. So effectively you are utilizing the CPUs, multiple CPUs. If you run maybe three different processes, they all can run. There is no lock business, and this is not going to stop you from running, as long as there are no other competing processes and only your processes are having higher priority. Then you have a free lunch. You can just occupy all the CPUs and run forever. Okay, so that advantage is there when you have multiple CPUs and you are running multiple processes, so you get that benefit. Okay, so the multiprocessing can be run on Unix and Windows. I'm not saying that it can't be run on Mac OS. Okay, it can be done. So in multiprocessing, processes are spawned by creating a process object. So we will see the example. You need to create a process object like a thread object we created, and then you you have to do the same start business, because if we create an object doesn't mean that they are running. It's like all the base work is done, but it is not at running. Okay, you have to do a start to make the process run. Otherwise it is available in the memory somewhere, and it's not at put into the CPU, or scheduler is not even aware of the existence of that. It's like your exe file sitting in your hard disk. OS will not do anything unless you say that I want to run a hello world or any program. Now then OS comes into play, and then they bring into the memory, and then they schedule it, and the scheduler is nice enough, it will schedule it on the CPU and your program runs. So all that will happen in the background from the OS. So now this is all what about multiprocessing. Let me see what I have for the next. Okay, that's all. Okay, so any questions before I go ahead with the example? Maybe I will go there, and I decided that to save time, I will directly show you the file. There is no copy business because small modules I have taken. Now, what I am doing, okay, let me show the code, then we will see. So, the multiprocessing module has queue, okay. This queue is different from the queue that you had within multi-threading, okay. It depends on the, I will tell you the reason why it is different. When you have multiple processes, okay, they want to communicate, okay, because they are in a different world. They have a different memory. They run in a different namespace. Okay, P1's namespace is different from P2's namespace. So they don't have anything common. Unless you create a shared memory SHM, and then you say that both of them can have an access, they live in a different namespace. Now if they want to exchange something, okay, now you cannot say that I will pass a pointer or some reference to the object which is here, okay, a reference to an object which is in this memory, okay. That may not work. It will work in a multi-threading environment, whereas it will not work in a multi-processing environment, because this memory, whatever you have, object memory, if you pass the address of this guy will not even know what it is, okay. Because again, I remember there is an MMU coming into play, memory management unit. Whatever the processor sees is a virtual memory, but what conversion happens to the physical memory is here. Similarly, this virtual memory, whatever you see, is a different part of the MMU register. Translation happens to this memory. So the memory address, maybe I call it as 1000, okay, or 0x1000. This 0x1000, whatever hexadecimal value address, virtual memory, whatever it says, is actually sitting here in some part of the main memory, physical memory. Whereas the same 0x1000 here is referring to something else here. Okay, they are not same. If I pass a reference 1000x here, it's, you cannot even say that it is going to access it. Okay, because even if it tries to access it, it's illegal. Okay, this process doesn't have any rights to access it unless both processes exchange information and say that you have a rights to access all my memory. Okay, which is normally done by a shared memory, where you can say that this part of the memory is mapped to both the processes and both of them can share it. Okay, again the address will be different. Okay, this process may say I am referring the starting address of the shared memory as 100. This may say that 200. Okay, that the virtual memory address may be different, but when it gets translated, it comes as a physical memory to the same location here, shared memory. So that's why if you know Linux, there is a mmap function which is used for mapping these addresses, because they live in different memory space. Okay, they were never namespace, or in language specifically they say namespace, but actually it translates to different memory space. So now how do we exchange information? So there are many ways, pipes you can use. Okay, named pipe or unnamed pipes. There you can pass one information and then it can be read by the other guy, or you can also pass actual content itself. Okay, you are not sending any references but complete information. Suppose if I want to say hello world from here, I will not send the reference to the string object. I send the whole string object down. Okay, so if I am sending the whole string object, it is self-contained. It's like packaging it everything and then giving it to the other guy, and then this guy can get that object, string object, and print it here, no issues. I am going to show you some example of that. So now what is the side effect? The translation, whatever you are doing, whatever is happening through the queue, is a much more than what you may do in this example. From multi-threading, if you are using a queue, you may just send a reference because the object is residing here. I don't need to send the whole object. I can send the reference to the object and I can still make the other thread to access it, because it's all living in the same memory space. But that is not true when you are having multiple processes. If you are exchanging information, you are in fact sending the whole thing, packaging it, copying it. Remember, you need to copy from this object whatever is the content into the memory queue, and then it has to be copied back into this and then consumed. So there is a lot of memory right, and then a lot of effort is there even when you are communicating across multiple processes. So you need to import the queue if from the multiprocessing, because I want this queue to be visible across multiple processes. When I say it is visible, P1 should know. If I say Q, maybe I call it as Q1, that Q1 is residing somewhere in the OS knows it, and then P1 sends it to Q1, and then P2 is taking it from here. Now, complete information is coming here, and the complete information is getting copied here. So, the Q1 is common. Okay, both of them, P1 and P2 knows Q1 and Q2. Okay, sorry, the Q1 object, whatever the Q1 is there, this Q is visible to OS, and it takes care of making sure that it is accessible to both. The Q is accessible to both. Okay, they don't reside in either in this P1 memory space or in P2's memory space. It resides in the OS memory space. It's like a OS resource. Q is a OS resource, like a file is a OS controlling the resource. You can share the file between two processes. You can share the queue. So one process will be putting the data, and another guy will be getting it from there. So it's a memory copy. Okay. So I am going to use that queue to exchange information between two processes. Now that is what I am creating here. Okay. Now this is the function. I call it as a different process. So this is going to be a function call passing a name, and I am passing Q1. Now what I am doing here, this though if it is a OS call and I am getting it directly from OS, I can say that the OS will take care of that. But still, each of those processes need to be aware of the Q1 because the Q1 is at the Python object. Okay, Q1 itself is a Python object. We have created it with the help of OS, but still I am exchanging it while creating the process itself as a parameter. Okay, so how do I do it? I pass the parameter here. Okay, name I am giving, And when I'm creating a new process, I'm saying this is your name, your child name, and then I am saying that use this queue which I created the queue object. Okay, this is the main thread or the main process which has created the queue, and then it is passing the queue as a parameter to it, so that when I use that queue to put some data, I can make it read by the other process, because this queue object is being shared, and the OS will take care of making sure that they are accessible. Somehow, the Python library takes care of it. So don't worry about too much about implementation details. Somehow this happens. I will tell you how it happens. The working of this. So now what I do, I am passing the Q1, okay, and then what I do, I want to see whatever I'm saying that this is a new process, right? I want to verify whether it's really a new process. So I am going to go get PID, and then now I want whatever is this process is printing, I can't get it on the main process. This is the child process. So I am sending the information, whatever is a PID that I get by running this OS interface. I create a, I print it here, but what I do is, I will tell you, in this case, you won't be able to view this messages. Later on, I will tell you how to get it. These messages are not visible right now because it is being given out by this process. You won't be able to see that here. And then what I do, this also I'll ignore it. Okay, please forgive me. This should not be there. Don't worry about it. Now I am passing the PID now. Okay, don't worry about this print. Though I have put it, I want to demonstrate that you won't be able to see this print, and I will show you how to get it now. Okay, I pass the PID. Okay, I get the PID here. This is the child process running, and it wants to know what is my PID, and I am passing it to the queue. Now this queue is known to this process also. Now let me explain one more thing. When this code is being run, what is happening is, this is understood when I am running this, the whole thing is the interpreter is going through this, but it is not executing this function. It is just understanding it. Okay, whatever is happening, okay, this function, it is goes through the function, and then it encounters this if name main. This is I don't know whether you guys are aware of it already or not, but let me explain what it is. Okay, actually I have not told about the module. Okay, let me explain. Now suppose there are many ways you can call your program, Python program. Suppose this Python program I have written, class py. Okay, now when I call this, when I say shift run or whatever I do here, okay, shift return here, it is running. Okay, it is running. Now how am I making it run? I am saying that this function, whatever I have, is given off to this. This is where the interpreter is running, and it is fed this Python file. Okay, it is say I am telling that please retake this file and run it here. So it runs whatever I give it. Now when I do this, it is actually initializing the name of this variable. Okay, this is a dunder file name. It initializes it with main. Okay, when I just run it like this, whatever I tell you. Okay, because I am running it on the Python interpreter, I am feeding the file and then saying that please run this Python file for me. Then Python says, okay, the interpreter takes your file, Python file, and it doesn't put the name variable, it doesn't initialize this name variable with the file name, it initializes with the main. Okay, now other way of running it, other way of using the same Python file. Suppose I have this, each Python file is a module, okay, from the Python perspective. So I am free to use this Python file as a import. I can import this as another module in some other file. I'm not giving the example here, but I can actually run this thing rather than as an individual file. I can import it on some other file. Suppose if I do so, if I don't run this file, I say, okay, not hash import, and then I say that session 15a mp1 cls. I don't mention the pi, it is implicit. Only thing is, when I do this import, this file, the .py file, should be available in the directory where I am invoking this interpreter from. So that is how do I know which directory I am invoking it from? Actually, if you print pwd, present working directory, actually the currently it is in this directory. Okay, so this file is not in that directory. I have kept it in somewhere else. Because the IDE allows me to run it, this file need not be in the same directory as where this um, interpreter is running from, because I have given the configuration here in the tools preferences that this is the directory the console is opening up. So if I import some file, it actually searches in the current directory where the interpreter is running from, or it has another variable which I may explain it later, Python path. Okay, just sorry, I shouldn't have opened it. Let me show you. Python path is another path variable where it searches for some of the import libraries that are there in the Python. So let me not go into the details of them. Maybe next week I will talk about some importing of modules and other things which are very important for you to know. Here, remember one thing. If you need to create a process, what is happening here is I am going to create a process using the process object, and then target I am going to say function. This is the function I want it to use it as a process. So you need to have this check, because multiprocessing module, which I am invoking it here, importing it, and I am creating the process, I am importing the process also, it needs this check. Okay, you need to put the process code, process creation code under the name main, equal to main. Okay, so why, I will tell you the reason. Okay, what happens is, when you are creating a process, first of all, you are running this main thread. When I say return, I am running this code once, and then the same file is fed to the another instance of a Python exe, and then a new process is created. I told you that two Python exes are created, right? So one Python exe is this console which is running this thread. Another one is another instance of Python exe which is going to again take this file as an input. Okay, so in that case, this name is not going to be main, it will be the Python file name. But interpreter knows that its new process is busy getting created, and it will handle it in a different way. So you will not have recursive way of creating the processes, because this code will not be executed when the same Python file is given to another instance, because that time the name will not be the main, it will be the file, this file name. Okay, this exactly this name will be given to this variable. So it will not go into this control and create another process. It will only use this function definition and execute this function, because already you have mentioned that the new process has to have the target as this function. It needs to have this function definition known to it. So this file is given to the interpreter, but because the interpreter is calling, we are calling it not like an import, we are doing it. So this name will not be same as the main. So it will not do another process creation, it will only do this job. Okay, so that's why you need to do this, and this is the reason behind it. I'm not sure whether I have made it clear to you in this short time. We can do it again on Monday, no problem. I don't want to force it and put you into your throat, but understand it clearly. Okay, think about it and run it, and then ask me any doubts on Monday. Now, what we are doing is, this is the main thread is going to execute it, because its name is main. Its job is to create. This is a parent process. Okay, its job is to create a child process. Now, this creation is happening, and I am passing a parameter, which is a name coming here, but I cannot see that because this is a different process and it is not connected to this window. So I won't get all the print coming here. Okay, I will show you how to get it. Now, what I do, I don't want to be completely unaware of what is happening there. So I am using a queue, and I want this child process to put its PID there, and I want to get it here. So I am using the Q1 get PID. That is what is coming here. Okay. Now main PID is this, child PID is different. Now these two are two different processes from the OS perspective. Now how do you believe it? Because you saw earlier also some PID, right? So let me show you how to trust my words. So I am going to make this child, when it starts running, it will send the PID, but it will not die. Okay. Now, if it doesn't die, what happens? Let us see. Okay. I'm sorry to say child dying and all that very bad words. Please don't. Maybe child doesn't terminate. Okay. That's a very decent way of saying that. So it is in the while loop. So it's not going to terminate. Now what happens is, this main thread is also running. Remember, this main process is also running, and this process is also running. This is also going to run forever. This is running in parallel in another instance, and it is going to print the child PID, which is it is printing, and then it is going to sleep for 2 seconds, and it is waiting for the P to join. What is P? The child process to join. Now child process is not terminating. So I told you that join will be successful only when the child process doesn't terminate. Now this is not terminating. So this guy is going to wait. So why am I making it to wait? I want to show you the actual these processes live in the OS world. So let us now run it again. Now you should have guessed it. What would happen? Going to join the child process, but it is not going to join because child has not been terminated yet. Now you can see now. Okay, the PIDs of both. Now child PID is 2236. So let me open my task manager, and then let us see the details. Okay, as already it is ordered. So where is 2366? It is there. Python exe. This is the child process running on this new instance of PVM. It's a new Python PVM running individually, still running because it is in the while loop. So it is not blocked. It is still running. Okay. So it's continuously doing nothing other than just looping around. Now, what about this guy? 10156. It is also available. You can see down the chain 10. Where is it? Okay, let me go down. Yeah, 10156. Sorry, 10156. This is also running on Python exe. You don't see actual Python file. Remember, it is running under the, from OS perspective, is only a Python exe is running. It doesn't even know that what Python file is running. Okay, from the OS perspective, but Python knows, and it is running. Now, how do I make this job, my parent to come out down? I need to forcibly terminate the thread. That not thread, it's a process. Okay, which one should I terminate? I should terminate this guy. How do I do it? Go forcibly kill 2236. I'm going to be a murderer now. Let me kill it. Okay, where is 2236? Right click, end task, end process. Now you see I have joined, child process has terminated, done. How? Because it was waiting for join. That means this process informed the OS, please inform me when that child process, I created it, I know I created it. When the child process ends, please inform me. So OS, it keeps in the zombie state, and then it looks for anybody waiting. This is waiting for that. So OS is informing this process to come out, and it comes out and prints it. So this is what is happening in this code. Any doubt on this execution? From anybody? Okay, we have 10 more minutes. I want to actually show you the other two pieces of code, which is exactly same, other than a new thing is getting added. Okay, I'll tell you what it is. I told you that I can't see anything that this guy is printing. Now I am very eager to know what is getting printed by that guy. Okay, now how do I do it? Very simple. Create a string. Okay, create a string whatever this guy is printing, instead of saying print, because once you do print, it is actually going to the STDIO, STD out, sorry, and which is not connected to my window. So it is lying somewhere, but I'm not able to see it. What do? I create a string object and pass it to the queue. Okay, whatever message I want, I pass it to the queue, same queue. So I like a PID, I am now passing the actual string which is getting printed by this process into the queue. And what do in the queue? I know the exact sequence what I am expecting from the by child. So I say child name is coming, PID is coming next, and the child PPID is coming. Now what I am doing is I am doing one more thing. Get the PID of yourself and tell me who is your parent. Okay, I want to know whether the parent child relationship proper or not. No, like a movie villain. I am trying to check whether this is really the this is my child or not. I am doing a DNA test. Okay, so I am checking its PID, and then I'm checking its PPID. Okay, get the PPID. See, I'm using the OS code because OS knows the process ID. Okay, not you and me. So, and how do I get it to the parent? I am using the same queue, get it here. Okay, so let us run now. And now one more thing is, I want to actually, I can decide not to do the while loop, or if you are really keen to know the processes, you can uncomment it and then go and check it in the background. Now to speed up the thing, I'm not making it run forever. Now let us clear this guy and run this. Now I am going to get the messages also from the child. So now you see here, main thread printed its own PID. This main process, okay, I should not use thread now. The main process printed its own PID, which is 10156. And then the child said, my PID is so and so, and my parents' PID is so and so. So I know the relationship. I only created the child, and then I am asking the child to tell who is your parent, and it says my parent is so and so. So it is established. DNA test is proved, and this is what is happening here. Okay, I am just getting the message as a from the queue, printing it here. So I hope this is clear to you. Now one more thing, what did I do here? Let me check whether I'm doing okay. I'm just trying to run it forever. Okay, it's very interesting exchange of messages between two guys. They sleep and then do. I'm sure you can read through this thing. What I'm doing is I'm creating two processes. Okay, I'm doing proc1 and proc2. Okay, and then I am asking them to send some 10 messages to the parent and then die. Okay, or terminate. Sorry, I'm very using bad words. So now let us see what is happening is two processes are created and their PIDs are different, and they run periodically. They send messages to the parent and they get printed. I get, proc1 is printing, proc2 is printing, and they get incremented. 10 messages they each of them they send, and then they terminate. And the parent also waits for both of them. It will wait for P1 to join, P2 to join, and then they done. Both the processes are done. That's all. Bye bye. So I created two processes. I made them to exchange 10 messages, and then I waited for them to terminate. I printed all the messages first. Okay, I went into the while loop. Okay, I went into the while loop, started printing all the messages coming from the child. I don't know who is getting, whoever is putting into the message, I'll get it. Okay, I don't know which process is giving. Both the processes are putting into the queue. Multiple processes can put, one process can read, and it can be multiple. No, anybody can read it as long as the Q1 is available. Anybody can read from it, or anybody can put the data into it. Okay, so two processes can put the data, and I can read it. So effectively, I have demonstrated how to run a multi-processing application and how to communicate between them using a queue. This is the summary of the today's class.